Okay, give that a shot. Whoa. All right. Okay, can everybody hear me now? Could you probably hear me before? Okay, but were there any questions about that? About the labs that have just run? Okay, well, so let's talk about the next sequence of labs. Let's start with the attenuation lab. Okay, so this is attenuation of gamma rays. So there are a few reasons that we're interested in attenuation physics. For gamma rays in particular, we're interested in shielding. You know, if you work with radiation at all, you're going to become very familiar with shielding to make sure you're safe in the experiments. And this it doesn't just apply to gamma rays. You've been to the dentist's office. They always put the lead shielding over you. And the purpose of that lead shielding is to attenuate out the X-rays so they can't do any harm to you. So anytime you're working with any kind of ionizing radiation, you're probably going to be figuring out some shielding situations. Okay? So yeah, let's talk a little bit about how this stuff works. So attenuation works just through interactions with the matter that you put in front of the radiation. And those interactions are the same interactions that you've studied so far throughout the gamma ray labs. So those interactions in our cases are the photoelectric effect, and the Compton effect. So these are discrete interactions. They're interactions where the gamma ray is hitting an electron or hitting or just glancing off of an electron and depleting itself of all or some of its energy, right? So you can imagine how that would work. You know, in a sodium iodide crystal, you have basically the same interactions, but in like aluminum or lead or some sort of shielding material, those are much denser materials, and these interactions are going to happen at a much smaller distance scale. Okay, so the purpose of this shielding material is to take all of the energy of that gamma ray and disperse it into the material via these interactions. Okay, so that's the basics of that. That's the physics of how it works. Now, so this is an exponential process, right? So it just means that the change in the intensity that you see is proportional to the amount of intensity that you started off with. So let's see. So we have the change in intensity as over the change in the distance is going to be proportional to your starting intensity. Okay? And this is an exponential process. So if I integrate this, same as the radioactive decay lab, I get that the intensity is equal to some initial intensity times E to the minus kx, where k is an attenuation coefficient. Okay? And so we'll call that 1 over the attenuation length. So that's the length where the intensity is 1 over E of its initial value. Now, there is a ton of physics in coming up with this value. Now, we can theoretically predict what this will be depending on what the actual interaction is. Okay? And the way we do this is by looking at the amount of stuff that's there, right? So we want the number of atoms per cubic centimeter, okay? Because these interactions are going to depend on the individual atoms, right? So if we look at the density of atoms, okay, as this. Now this is the density of the material times Avogadro's number over the atomic mass, okay? And so that gives you the density of the number of atoms per cubic centimeter, or the number density of the material, okay? And we're going to multiply that. So this is a density. We want something that has units of inverse length, all right? So our factor here that we need to multiply by has to have units of area, okay? So this is where we're going to introduce the scattering cross-section. Can you all see this okay? Okay. All right. So this scattering cross-section has a ton of physics in it. It's very, very phenomena dependent. So in the lab write-up that you're going to see, you'll have several different scattering cross-sections. So I'll give you an example of one, if I can find it. So if you're just looking at Thomson scattering, which is related to the photoelectric effect. Okay. So that's the scattering cross-section for Thomson scattering. So there is a lot of theoretical development into deriving a proper cross-section, depending on the physics phenomena that you're looking at. Okay, there's a lot of it in Melicinos. There's some of it in the lab write-up. It's honestly kind of beyond the scope of the course. Okay, but you should know it's there. All right, you'll see it in more advanced classes. You'll actually go through and derive these different scattering cross-sections. There's a ton of work to be done in there. But for our purposes, we're just going to say, okay, we have this scattering cross-section. Let's deal with it. Let's get to this value right here. This is what we're interested in for the purposes of this class. Okay? So our task is to figure out what the transmittance is for a given material. In our case, we're going to look at aluminum. So what we're going to do is we're going to take our gamma ray source, the same gamma ray source we've been using throughout this sequence of labs. We're going to take that source, and between it and the sodium iodide detector, we're going to put a few different pieces of aluminum of varying thickness. Okay? So we're going to take a 5 centimeter piece, a 10 centimeter piece, a 15 centimeter piece, a bunch of different lengths. And then we're going to accurately determine what this attenuation coefficient is. Okay? So that's the purpose of this lab. Oh, yeah, I wanted to talk a bit about transmittance. So we're not going to look at the intensities because we don't know the area. That doesn't really tell us a lot. So we're just going to look at straight up transmittance. So what do I mean by transmittance? The transmittance is just the amount of light you get out over the amount of light you put in, okay, for any sort of light, visible through gamma rays, okay? So that's very closely related to this, right? Okay. Now, in our experiment, which is not perfect, all right, we're going to have some background. You already looked at the background in the gamma ray decay lab. So for our purposes, we're going to look at the amount of light measured, which we'll call y, minus a background that we'll also measure, and look at that over our I0, which we'll measure. So that we'll measure without any sort of material in the path at all, also minus the background. Okay, so this is actually the measurement you're going to make. And from that, you can back out what kappa is. Okay? And of course, there's some fun statistics in there, but we'll get into that in the lab. Any questions? Okay. So next, let's talk about the Planck Law experiment. Okay. So I really consider this like the granddaddy of all modern physics experiments. It's just completely fundamental to the development of quantum mechanics. And it comes out of the study of black body radiation. So what's a black body? Someone tell me? A black body is what we call a perfect emitter. Okay? Basically, it just means that it doesn't, when you look at a black body, you don't see any light reflected from any other source. The light is purely coming from that source. So the classical example of a black body is a box with a hole in it. Okay? So this hole is very small. All right? The sides of the box are perfect absorbers. So any light that hits any side of the box will be absorbed by that box. So if I send in light from the outside, it's going to be absorbed. If I have light that's emitted internally and it hits the sides, it'll be absorbed. Okay? So when you look at the light coming out of this with the detector, you don't see anything but the light emitted from the inside of the box. Okay? With no reflections at all. Okay? So you're looking at a pure transmission. Okay? No reflection at all. All right? So why is this useful? Well, if we heat items up to a given temperature, we notice that it starts to emit light, right? So what we're explaining here is like you have a hot poker in a fireplace, right? You see that it glows red hot. You see that as you let it stay in that fire for longer periods of time, it gets whiter and whiter and whiter, or bluer and bluer and bluer, right? So the spectrum of that emission changes as you continue to heat up that object, right? So that's what the Planck Law describes, is how that process works. It also describes how a light bulb works, right? So the light bulb is what we're going to use in our experiment. So the actual physics of this was very tricky at the time. So the Rayleigh-Jeans law The Rayleigh-Jeans law was an attempt to show how classical physics really fails at describing this phenomenon. It was derived from purely classical mechanics means. So basically, they took this box and said, OK, well, what we're going to do is we're going to describe the energy in this process as a bunch of standing waves, right? So we're just going to use the wave description of light. And so we're just going to set up standing waves in this box and use that to describe the energy density of the light. Okay? And so the result of that was a distribution function that looked like this. Yikes. Okay? So this is the Rayleigh-Jeans law. And what this looks like is this. So you've probably seen this before. And what this gives you is what's well known as the ultraviolet catastrophe. Okay? So this fits the data really well at large wavelengths. But as you get to shorter and shorter wavelengths, it diverges. So this says that the intensity of radiation for a black body should approach infinity towards the ultraviolet wavelengths, okay? Which doesn't make any sense, right? The world would be completely wrecked if this were the case. What we actually see is something closer to this. Okay? So this is what we actually see. And it wasn't until Planck came along and took a different tack to the problem. He said, OK, well, we can't really use the standing wave in the box model because it clearly doesn't give the right result. So what we're going to do is we're going to, instead of treating the photons as waves, we'll treat the photons in this box as a gas of particles. And a gas of particles, each one of those particles has an individual energy, right? So Planck said that, OK, if we say the particles have energy h nu, and we treat this as a gas of photons, then we can apply Boltzmann statistics to the problem. And so Planck was really quite the genius, and experimentally determined that this function works. And the actual theoretical derivation of this didn't come along until much, much after. But the experiment came up with this. So the same energy distribution. Oh, HC over lambda. That's never going to show up. So this function provides a perfect match to this. And so this was just completely revolutionary, okay? Because using the particle description of light clearly matched the data. So this is when people really began to pay attention to quantum mechanics as a theory, okay? So what's our job? Our job is to verify the Planck Law, okay? And so We're actually going to do that with equipment calibrated using the Planck Law, but I won't really get into the philosophical difficulties of doing that. So here's what we're going to do. So we don't have a black body. We can't look directly at the cosmic microwave background, which is a wonderful black body. We are going to use a tungsten light bulb filament. Okay? The only difference between a tungsten light bulb filament and a perfect black body is that here we have to introduce a constant called the emissivity. All right? Because a tungsten filament will have reflections coming off of its surface, it's not a perfect black body. We have to put this multiplicative factor in here. Okay. And for a tungsten filament, it's about 0.3. A perfect black body has an emissivity of 1. Okay. So we're going to look at this light bulb filament. Okay. And we're going to look at it using a device called an optical pyrometer. All right. So an optical pyrometer is just a telescope. All right. So we're going to point this telescope at this filament. Now, on the inside of this telescope, there's a reticle. And you know, if you've ever used a spotting scope or anything like that, a reticle is just like a crosshair. In our case, it's a little U-shaped wire. Okay? Now, the nifty thing about this wire is that we can heat it up to a very well-calibrated temperature. Okay? So we can dial this in at a very specific temperature, which was calibrated using the Planck Law, by applying a current to it. Okay? So what we're going to do is we're going to look at the color of this with our eye and match it up to the color of this filament. So we'll drive this filament with a given current, and we'll look at it through this telescope and determine the temperature of it. Okay? So that's using an optical pyrometer. Okay? And that will give us the temperature as a function of the current through the tungsten filament. Okay? Now, you might have guessed that this filament is actually attached to the light source that's used in the photoelectric effect, and we're going to look at a light of a very specific wavelength through the monochromator. Okay, so very similar to the photoelectric effect, we're going to look at the intensity of the light coming out of that light source with a photomultiplier tube. So we're just going to take the photoelectric cell off, put a photomultiplier tube on, and we'll look at the intensity of that light at a specific wavelength directly. So the monochromator will give us the intensity at a given wavelength as a function of current. Okay? And so using these two pieces of information, we can back out this curve. Okay? So that's our task. All right? And I promise it goes much smoother than the photoelectric effect lab did. Is there anything else I needed to say about that lab? I don't think so. Does anyone have any questions? Please have questions. No? All right. Well, then we'll keep this short and sweet. Okay? So I'll stick around for a while longer if you have questions about your labs. If you want to talk about the class, I'll be here for a while. But okay, I'll see you all in lab. Thanks for coming.